Hello and welcome to grade 12 4U Physics, and this is the first lesson of the course. We are starting into unit number 1, and the unit is dynamics. So today I'm going to cover a variety of past material, so it is a review day. So what's the goal today? I want you to be able to explain and apply concepts, free body diagrams, and motion previously learned in your 3U or your grade 11 course. So jumping right in, one of the important things we're going to be dealing with in the first two units, we need to be able to draw effective free body diagrams. Keeping it simple, the object is reduced down, so I'll just put it over here. Object is reduced to a point. All right, and all forces, and in brackets, I should put vectors really, but all forces are vectors. Actually, no, let's not do vectors because we are doing free body diagrams. So I'll keep it like this. So all forces are drawn with tails connected to the point. All right, arrowheads are added. Arrowheads are added to vectors for direction. And finally, the name or magnitude should be labeled. So name / magnitude should be labeled. All right. So getting caught up with the diagram then, what would I like to see? I want to see some of the forces and some of the ones just as a reminder from from the 3U course. For example, if I have my unbalanced force, it's clearly labeled, it shows the direction acting on the object. Whenever you have an unbalanced force in a particular direction, you always have an opposing force, and it's force due to friction. Any object that is on the planets, or for that matter anywhere, will be acted upon by the force due to gravity. And if this object is sitting on a table, there may be a normal force. So there are some examples. Those can be labeled. If you know the particular value, you can include that inside the diagram, or you can list it below. It's whatever you prefer. So M, and as a note for the grade 12 course down here, I'm going to use gravity equal to 10 meters per second squared. That way it makes it a little bit more simpler, and it's just a nicer number to work with. I know it's 9.81, but it varies depending on where we are on the planet. 10's a nice number. Engineering background coming out in me, it's a close approximation. It's kind of good enough, and we're over approximating, so there's a safety factor in there. All right, so moving along then. Let's talk about some previous terms here. So scalar versus vector. So we do use vectors extensively through the grade 12 course, and I told you in grade 11, very important to get this nailed down. So we do have scalar versus vector. Scalar, definitions there for you. It has magnitude, and that's the word I'm looking for, is magnitude. So distance, speed, and mass. A vector has both magnitude and direction. All right, so we've got one with just magnitude, and the other one has both magnitude and direction. And we have examples: displacement, velocity, acceleration. So let's talk about some of the common vector / scalars we're going to be dealing with in this particular course for this unit. So the first one down below here, we're going to be talking about distance and displacement. Very important that you differentiate between the two, or can explain the difference. So for example, distance is a measure of length, so kilometers, meters, miles, depending on where you're planning on working in the future, whereas compared to displacement, which is a measurement of length and direction. So a couple of simple examples here: 20 kilometers, 30 meters. Down here, I would have 20 kilometers, and we could be labeling it as forward for F, or the 30 meters could be north 20 degrees east. So it's very important that we remember the difference between them. And if I ask a test question and I ask for displacement, it's important that you give me an answer with length and direction. So that's where it starts to come into play. I'm not going to be asking you any longer for length and direction. I'm just going to say I want the displacement. And as a grade 12 course, the expectation is that's what you provide me when I ask for a vector. Next one, speed versus velocity. So another very important one to be able to differentiate between. Speed, again, is a measure of distance in a given amount of time. All right. So our formula for that really all stems from d equals vt. Okay. And that's your distance. Oops, I shouldn't have the vector arrow on there. When we're talking about scalars, it's just d equals vt, where d is your distance, v is your velocity or your speed, technically. T is time. Whereas its partner, velocity, is a measure of displacement. It's the same formula when there's no acceleration. The difference is, or how you know the difference, is that the vector notation is there. So now I'm dealing with displacement instead of distance. So just as a reminder, when you're going through and watching the notes, d is your distance. If it has the harpoon above it or the vector notation, it's your displacement. So you got to be very careful. It's the same thing when you're writing concluding statements or you're writing a solution for me. Do I need the vector notation or not? All right. Similarly, I'll do the other one. If it just is a v, it's just speed. If it's a v with the arrow or the vector notation, it's a velocity. That way we maintain the same equation. It's not confusing. Then you know it's going to be the same equation. So this more speaks toward your communication mark. Okay? So this is where, when I'm looking at communication on a test or an assessment, I'm focusing on, did you use vector notation where appropriate? Did you use scalar notation where appropriate? So just keep that in mind. Next topic I want to talk about is acceleration. As it was from the grade 11 course, it is the change in rate of velocity or speed in a given time. Now it should be velocity technically here because acceleration is a vector. You do have to give it a direction. So I'm going to cross out the speed for argument's sake here. All right, and our units. Remember, acceleration, when you did a D or a VT graph, you did the change in velocity with respect to time. When you do a unit analysis of that, velocity is a measurement of meters per second. Time is in seconds. Using your math skills, that's meters per second squared. All right, so units for acceleration, meters per second squared. Okay, and again, it is a vector, so you do need direction. All right, so it is important that you include a direction. Am I speeding forward or increasing my velocity forward? Am I decreasing it, and so on and so forth. 5 equations of linear motion. So these are the ones from the grade 11 course. It was the first unit. You had to use them again in the second. So you have your non-acceleration or uniform motion. So velocity times time. So beside that, I'm going to go uniform motion. All right. If you have acceleration, then we have a series of equations that helps us with that. We have v2 equals v1 plus a delta t. We have v2 squared equals v1 squared plus 2a delta d. What else do we have here? We've got our displacement, delta d equals 1/2 of delta t multiplied by v2 minus v1. Oops, minus v1. And finally, delta d equals v1 delta t plus 1/2 a delta t squared. So there are the 5 motion equations. These 4 deal with non-uniform motion. So that means that acceleration is not 0 meters per second squared. Up here, I guess we could put that addition on, that acceleration is going to equal 0 meters per second squared. All right. So there are the 5 equations that are required. Again, you get a cheat sheet, so make sure they are correct on the cheat sheet and make sure they're labeled accordingly, uniform versus non-uniform. So a couple of examples here. And to start off with, it's very similar to grade 11 course. We're just going to look at some decoding to start. So a bike is traveling at 12 meters per second west. So I have a velocity, 12 meters per second west. She changes gears and speeds up. So that means my velocity is going to change. So I'm going to put a subscript on that first velocity to say that was the initial of the first one. A time has passed. So 3.5 seconds have passed. And it gives us an acceleration of 5 meters per second squared west. We want to know displacement. So we are looking for delta D. So it becomes, like I said, it's a decoding process. With any of those equations, you need 3 pieces of information to find a fourth. We know V1, delta T and A. So you go through and do a process of elimination, and we see that last formula that I wrote there is going to be the one that's going to help us out. So delta D equals V1 delta T plus 1/2 A delta T squared. Don't have to rearrange it. It's in the proper format for us. So we get 12 times 3.5, 1/2, acceleration is 5, and T squared. Now, at this point in time, I just want you to hold up for a second and just note that because velocity, or V1 was west, acceleration is west, that means that when you enter that information into your equation, they have the same sign. So my assumption here is that west is positive. All right, so I'm just going to put that down here. You don't have to do that for every question, but heading west, I'm going to assume is the positive direction here. All right, that way when I'm doing the calculations, everything's in agreement. If it was something was east, you'd have to change the sign or symbol. So we get 73.2 meters. Displacement is a vector. If everything was west, I assumed a positive answer will then give me the positive direction. So therefore, bike traveled 73.2 meters west. There's your final answer. Moving along. Curling stone slides on the ice and accelerates at 5 centimeters per second north. So we're given an acceleration 5 centimeters per second north as it travels 28 meters south. So now we know a delta D, or a displacement, 28 meters south from its original position before coming to rest. Determine the initial velocity. So we know V1. Sorry, we want to know V1, my mistake. And we have 2 pieces of information. In order to solve a problem, we need to have 3. So I'm going to finish this in the next video, and we'll pick it up from there. We'll see you in a second.